In the last lecture, we talked a lot about concepts from physical chemistry. We talked about basic physical concepts, things like how things propagate through the environment, how molecular communication compares with wireless. We talked quite a bit about energy, and we came up with some ways to think about how to create a molecular communication transmitter. So in this lecture, what we're going to talk about is some physical concepts that are very important as far as how molecular communication is accomplished at the molecular level, and that is by chemical reactions. So in this lecture, we're going to talk about chemical reactions. So the most important thing to think about, or the most important thing to do first, is to define what we mean by a chemical reaction. So a chemical reaction is a transformation from one chemical species to another. And depending on when you took your last chemistry course, which could have been some time ago, for me it was at least 20 years since I personally took my last formal chemistry course, you probably remember chemical equations. So often, chemical reactions are represented in chemical equations. And you may remember what chemical equations look like, but just to get back in the swing of things, let's see an example. So for example, a combustion reaction. Let's say we have methane, and we react it with atmospheric oxygen. So this is a straightforward reaction. The product of any combustion reaction is carbon dioxide and water. And one thing that's important is to make sure chemical reactions balance out. Again, you might remember this from the last time you took a formal chemistry course. But the idea is that the total number of atoms on one side must equal the total number of atoms on the other side. So I won't go through exactly what is going on here. I'll only verify, but it turns out to make this balance, one molecule of methane plus 2 molecules of oxygen will produce 1 molecule of carbon dioxide and 2 molecules of water. And it's pretty easy to see how this works. So, I mean, in a chemical reaction, it's important to note that atoms are neither created nor destroyed. 1 carbon here, 1 carbon here, 4 hydrogens here. We have 2 times 2, which is 4 hydrogens over here. We have a total of 4 oxygens right here. And on the right, we have 2 oxygens in here, and 2 times 1 oxygen is another 2 over here. So it's 4 oxygens. So everything balances out. So chemical reactions balance. One point to take away here. Another is that species are transformed. So again, by species, I mean, here we have methane, here we have oxygen, Here we have and that's transformed into carbon dioxide and water. But it should be clear that atoms remain unchanged. If the atoms changed, then we would no longer be talking about a chemical reaction. We would be talking about a nuclear reaction, which is not something we're going to be talking about in this course. All right, so that's just, we're not going to actually see any, in general, we're not going to see any specific reactions like that. So in general, we will treat reactions abstractly. What do I mean by that? So instead of a second ago in the example, if I go back, we had molecules that we've heard of. So methane, oxygen, carbon dioxide, and water. Over here, we are not going to deal with chemicals, or excuse me, molecules that have names or well-defined chemical formula. We're just going to be dealing with them as symbols. So you can just think of them almost algebraically. There are good reasons for that. One is we're going to be dealing with complex biomolecules that are difficult to express in terms of chemical formulas, or even impossible to express in terms of chemical formulas, but we still want ways in which to talk about the reactions. Another is that these reactions have basic forms that are very consistent across different kinds of molecules. They work in kind of the same way, and we want to manipulate them in kind of the same way. Again, it's very similar to why we use algebra. All right, so to get the ball rolling here, let's talk about some basic kinds of reactions. Oops. Sorry for the screen jump there. And to sort of see this algebraically, we can imagine a kind of reaction using a molecule A plus a molecule B that form a compound AB. This we're going to call a synthesis reaction. Basically, we take some A, some B, and put them together. Going the other way, if we start with some compound AB and break it up into its component parts, that's called dissociation. We're going to see examples. We're actually going to deal a lot with synthesis and dissociation. So, for example, synthesis, that could be the binding of a signal molecule to a receptor. And dissociation could be the processing of the signal molecule. Returning the receptor to its ready state. In other words, what we might think about is that this reaction, if you imagine the receptor looking like this, signal molecule is coming along and might find its way into the receptor, forming a compound. We're going to call it compound AB. So this is the signal molecule A. This is the receptor B. when they come together, we're going to call that AB. Then later, oops, while they are bound, eventually when they are bound together, then they are the compound, and eventually this bound molecule is going to leave. Either it's going to be processed or it's going to be somehow ejected, and then you will have back the unbound receptor and the signal molecule, and then the unbound receptor will be ready for another synthesis reaction. So there's two concepts that are important here. One is reaction rate. So if I have, let's say, a synthesis reaction, I might write the rate on top of the arrow like so. And that basically, you can think of it, depending on how the units work, you can think of this as the number of reactions per second. It could also, R can be dependent. So R can be the number of reactions per second, and R can be dependent. Actually, let me go further. R is generally dependent on the concentrations of the reactants here, A and B. Okay, just a quick note about notation. If you see square brackets around a chemical species, that is the concentration of A, and we will generally talk about concentration in terms of molar concentration. Now again, you might have to think way back to your last chemistry course about this, but molar concentration is not that difficult a concept. Excuse me, actually, this is something different. We're gonna use molarity, by which we mean moles per liter. And remember that moles is, it's just a counting unit. It's the number of multiples of Avogadro's constant. So in other words, if you have exactly Avogadro's constant of A, then you have exactly 1 mole. If you have exactly one mole of A dissolved in 1 liter of water, then the molarity of that is 1. Okay. Second concept to note after that digression about notation is reversibility. And this should have been clear from, or actually this is implied by my definition of the two fundamental reactions that we're going to talk about, synthesis and dissociation. But it is generally true that most of the reactions we talk about are reversible. not all, but in general, most of these reactions are reversible, and there will be a forward rate. So there are many terms for the forward rate, but often you'll see something like K plus, and then the reverse rate, K minus. So in other words, what is happening is that A and B come together to form AB, but as you form AB, the compound AB, it can dissociate into A and B separately. So while these guys are forming, these guys are dissociating at the same time. If you think about what that means a little bit more, what it actually means is that eventually these systems, these chemical systems, will come to some sort of steady state where the forward rate and the reverse rate balance out, and the system no longer changes. All right, so we've talked a lot about kinetics. Now it's time to actually analyze these systems mathematically. And the method by which chemical reactions are analyzed, well, one of the principal ways is through a principle called mass action kinetics. So under mass action kinetics, reaction rates are proportional to the concentrations of the reactants. So in a synthesis reaction, if I have a certain rate, A plus B to AB, the rate of that forward reaction will be some constant. I'm going to call it K plus. Again, that's my forward reaction rate constant times the concentration of the two reactants. Again, I will write, so earlier in the last page, I wrote the actual reaction rate on top of that arrow. And then down here, I wrote something different. I wrote these Ks, which are actually the reaction rate constants. The correct idea, so I did that over here just for illustration. I did this for illustration, but this is actually correct. So what you'll see is that it's the reaction rate constant that ends up on top of the arrow. And what the reaction rate constant means is that it's the constant proportionality multiplied by these concentrations. Similarly, so that's for synthesis, similarly for dissociation. And again, the symbol I used over here was K minus, so the rate of that reaction, K minus, times the concentration of the reactant over here, which is just AB. It's the concentration of that compound. So you can, now we are starting to form the basis of mathematical analysis of chemical reactions. And the most important thing that we're going to think about is how these reaction rates can be used to form differential equations. So if you imagine, so mass action kinetics can be used to form differential equations. representing the dynamics. Oops. The system. This will become important later, but for now, let's just treat this very simply. So imagine we start with, actually, let me back up just for a sec. Consider a synthesis reaction. So in a synthesis reaction, what we would have is AB, or A and B, forming a compound AB with a positive, excuse me, a rate coefficient of K plus. All right, so if I look at the concentration of AB at time t, and then I'm interested in the concentration of AB at some later time, let's call it t plus delta t. What's the difference there? So what we could write is the change in that concentration. You can probably see where this is going. Excuse me, that should be a minus. Sorry, let me just back up here. What will that change be? Well, we have these individual components A and B, and they are forming the compound AB. The rate of that reaction is given by R equals K plus times the concentration of A times the concentration of B. So we might expect that over a short period of time, if delta T is sufficiently small, this is the rate, in other words, the number of reactions per second, we would sort of expect that that would be K plus concentration of A, concentration of B times dt. In fact, what we can do now is we can take the dt over here and we can say AB at t plus delta t minus AB at t divided by, sorry, I kind of gave the trick away there. That should be delta t divided by delta t is equal to K plus A B. And then as delta t goes to 0, well, as delta t becomes very, very small, we generally call that dt. In the numerator here, this is the change in AB. So we would normally write this as d AB divided by dt is equal to K plus AB. And you can do this for any chemical reaction you like. The reaction rate, which is given by the concentrations of the individual components, and the rate constant is going to define the change in the concentration of the product. So generally speaking, you can look at a chemical reaction such as this and then write down its differential equation. That's going to let us do a couple things here. Actually, let me just back up for 1 second. Now look at this equation. If both A and B are changing at the same time, then this differential equation, so what's going to end up happening is imagine also the reverse reaction. Then we'll have the change in concentration of A and the change in concentration of B. as a function of the concentration of AB. Now, we have a product of AB here. So in that system of equations, this will end up being a nonlinear differential equation, which is not great. Let's first consider a simpler system. I'm just going to have, and this kind of system will actually come up kind of a lot in very simple ways. So I'm going to have some compound A that can transform itself into B and come back. Remember, these are abstract. So this forward reaction could actually be dependent on something else. So in other words, I could add something here, but it would be something at constant concentration, so I don't really have to worry about it. But just imagine that I have a very simple system of one chemical species transforming itself into another and coming back. And in fact, you could even think of this as a folding protein. So we could have a protein that is folded like this. That could be A. And then the protein stretches itself out. We usually talk a little bit about what I mean by protein and folding, but you could just imagine this as two different states of one system. It doesn't even have to be a chemical system, it's just two different states of one system. Using what we just talked about, I can represent this system as a system of differential equations. So if I take A to produce B, I can write down this differential equation, dB by dt is equal to K plus times the concentration of A, and dA by dt is K minus times the concentration of B. Okay, this all makes sense, remember? A produces B, so the amount of change I get in B is dependent on the forward rate, which is the concentration of A times K plus, and the reverse reaction, B turns into A, there's some rate constant K minus, so the change in A is K minus times the concentration of B. So this is quite consistent with what I just talked about. If you look at this even more closely, this is a system of two linear differential equations, and I can actually represent this as a matrix, or in terms of a matrix. Now here's how it's going to work. The change in B is going to be K plus, excuse me, that K plus rate. So the amount of B that I get afterwards is the amount of B that you start with plus K plus times A. So you know, I must have to remove K plus from A, and similarly, this amount of B transforms itself to A, so I must have to remove this amount of B from B. So I end up with a matrix equation that looks like this. So d by dt of A and B is equal to some rate matrix. Now, what I just mentioned, that's going to go into the rate matrix times the concentration of A and the concentration of B. So it's pretty clear how these elements of the rate, how these elements fit into the rate matrix. So let me write that. So R will be equal to, all right. Now, if I'm just gonna sketch this over here just to keep myself in mind of where I'm going with this. So d by dt of A and B is the rate matrix times A and B. So what I start with for, what I end up with for B is K plus times A. So ending up in B, I have K plus, and if you imagine, so I have this row of the rate matrix multiplied by this column, so I have K plus times A. And similarly, to get this, the change in A is K minus times B. In order to get that, I need K minus here. And then if I multiply this row of R by here, I get K minus times B over here. One feature of these rate matrices is that these diagonal elements have to make the columns sum to 0. And that's what I mentioned a second ago. So the amount of A that escapes from A is equal to the amount that reacts into B. So that means that the amount that reacts into B is K plus times A. So that amount must leave A. So the amount of A that leaves A is K minus because it becomes B. And similarly, this column also has to sum to 1 for the same reasons. That's minus K minus. And the reason is, when you multiply this by here, K minus times B, that's the amount of B that becomes A right there. So we end up with a differential equation, d by dt, concentration of A, concentration of B is equal to my rate matrix. I'm just going to put it back to make sure I'm getting this right. Like so. This is called the master equation for the system. We're going to come back to master equations later. But one interesting feature of the master equation is the following. If I come back here, if you think of these as two states of a discrete time system, or even a continuous time or discrete time system, but two states of a finite state system. The rate at which you go from here to here, if you have only a single molecule A, rate at which you go from here is transition from this state to this state. And similarly, the rate from here to here is the rate at which you transition from this state to this state in the finite state machine. This actually becomes, as we will see later, this actually becomes a Markov process. So you can make a transition from here to here at a certain rate or a certain probability in discrete time, and from here to here. And what we're going to see is that this rate matrix and the master equation give you exactly the transition probability matrix for the discrete time Markov chain. So this will lead to this. Again, we're going through some fairly intense theory right now. The important thing to remember here is that this will all become very relevant later. But the important thing to remember here is that you can form this master equation simply from this this reaction by forming these reaction rates. And what you end up with is a system of linear differential equations with these rates. You plug in the rates where they go and just make sure the columns sum to 0. And then you have the master equation. Eventually, like I said, this rate matrix will become important in terms of the Markov analysis of these systems. In the next lecture, we're going to look at the eigenvectors and eigenvalues of the master equation and how they relate to the steady state solution, among other things.